You know, there's something deeply romantic about Mars. Something that captures the human imagination in a way that few other celestial objects do. It's right there in the night sky, a reddish point of light that's been visible to humans for as long as we've looked up. Ancient civilizations named it after their gods of war. Science fiction writers have populated it with canals and civilizations. And for the past century, we've dreamed of going there. Elon Musk wants to build a city on Mars. NASA has detailed plans for crewed missions. SpaceX is developing the Starship specifically for Mars colonization. The rhetoric is confident, even triumphant. Mars is the next frontier. Humans will be a multi-planetary species. We'll have boots on Mars within a decade or two. And I want to believe this. I really do. The idea of humans walking on another planet, establishing a permanent presence beyond Earth, becoming a spacefaring civilization, it's inspiring. It speaks to something fundamental in human nature, the drive to explore, to push boundaries, to venture into the unknown. But here's what I'm going to tell you today, and I want you to really hear this. Reaching Mars, actually putting humans on Mars and bringing them back safely, let alone establishing a permanent settlement, might be impossible. Not impossible in the sense of difficult or challenging or requiring significant technological advancement. Impossible in the sense that the laws of physics, biology, and engineering might simply not permit it with anything remotely resembling current or foreseeable technology. Now, I know that's a provocative statement. And I'm not saying this to be a pessimist or a naysayer. I'm a physicist. I follow the evidence. I look at the numbers. And when you actually work through the physics of a Mars mission, when you calculate the energies involved, the radiation exposure, the biological effects, the engineering challenges, you start to realize just how staggeringly difficult this is. So let me take you through it. Let me show you why Mars, despite being our closest planetary neighbor aside from Venus, despite being visible to the naked eye, despite seeming so tantalizingly close, might actually be forever beyond our reach. I'm going to tell the story in 3 parts. In part 1, I'm going to talk about the distance and the energy requirements, why getting to Mars is so much harder than most people realize. In part 2, I'll discuss the radiation problem, which might be the single biggest obstacle to human Mars missions. And in part 3, I'll talk about what happens if we actually make it to Mars, the challenges of survival on the surface, and why coming back might be the hardest part of all, the deceptive proximity of Mars. So let's start with distance. Because when people think about Mars, they often think it's not that far. I mean, it's the next planet out from the sun. It's our neighbor. How hard can it be? Well, let's put some numbers on this. The distance from Earth to Mars varies considerably because both planets are in elliptical orbits around the sun. At its closest approach, what we call opposition, when Earth and Mars are on the same side of the sun, Mars can be about 55 million kilometers away. That's about 34 million miles. At its farthest, when we're on opposite sides of the sun, Mars is about 401 million kilometers away, roughly 250 million miles. So the distance varies by a factor of 7 depending on where the planets are in their orbits. This means you can only launch a Mars mission when the planets are favorably aligned, which happens roughly every 26 months. Miss your launch window, and you wait over 2 years for the next one. Now, 55 million kilometers sounds like a lot, but let me give you some perspective. The moon is about 384,000 kilometers from Earth. So Mars, at its closest, is about 140 times farther away than the moon. And we've been to the moon 6 times, in fact, between 1969 and 1972. 12 humans have walked on the lunar surface. So if we could get to the moon with 1,000 960 seconds technology, surely we can get to Mars with 21st century technology, right? Wrong. And here's why. Distance in space is not just about kilometers, it's about energy. And the energy required to get to Mars is vastly, enormously, overwhelmingly greater than the energy required to get to the moon. See, when you're traveling in space, you're not fighting air resistance like you do on Earth. There's no air. You're fighting gravity. Specifically, you're fighting the gravitational pull of Earth, which wants to keep you from leaving, and you're also working with and against the gravitational pull of the sun as you travel between planets. The key concept here is something called delta V, which is short for change in velocity. It's a measure of how much your spacecraft needs to change its speed to accomplish a mission. And delta V directly translates to fuel requirements through something called the rocket equation. To get to the moon and back requires a delta V of about 15 kilometers per second. That's already enormous. You're talking about accelerating to speeds that are about 50 times faster than a bullet. But to get to Mars and back, you need a delta V of about 30 to 40 kilometers per second, depending on the exact trajectory you choose. That's roughly double the moon mission. Now, you might think, okay, double the delta V means double the fuel, right? Wrong again. And this is where the rocket equation becomes absolutely brutal. The rocket equation, first formulated by Konstantin Tsiolkovsky in the 19th century, tells us that the amount of fuel you need grows exponentially with the delta V you're trying to achieve, not linearly, exponentially. Here's why. To accelerate your payload, you need fuel. But that fuel has mass, which means you need more fuel to accelerate the fuel. But that additional fuel also has mass, so you need even more fuel to accelerate that fuel. It's a vicious cycle. The upshot is that doubling your delta V doesn't mean doubling your fuel, it means squaring your fuel requirement or worse. In practice, achieving twice the delta V might require 4 times or 8 times or even more fuel, depending on your engine efficiency, and this creates a fundamental problem. The more fuel you carry, the more massive your spacecraft becomes, which means you need even more fuel to lift that fuel off the ground in the first place. You quickly reach a point where the spacecraft is 90%, 95%, even 98% fuel by mass, with only a tiny fraction being the actual payload, the crew capsule, the life support systems, the scientific equipment. The Apollo spacecraft that went to the moon was mostly fuel. The Saturn V rocket that launched it stood 111 meters tall and weighed 2.8 million kilograms when fully fueled. Of that, only about 45,000 kilograms, less than 2%, was the command and service module that actually carried the astronauts. And that was for a moon mission. For Mars, you'd need something far larger, far heavier, far more complex. Now, you might say, well, we have better rockets now, more efficient engines. Surely that helps? It does, somewhat. Modern rocket engines are more efficient than the ones used in the Apollo era, but the improvements are incremental, not revolutionary. We're still using chemical rockets, burning fuel and expelling the exhaust to generate thrust, just like we did in the 1,960 seconds. There are more exotic propulsion systems in development, ion drives, nuclear thermal rockets, even theoretical concepts like nuclear pulse propulsion or antimatter rockets. But none of these are anywhere near ready for a crewed Mars mission. Ion drives are incredibly fuel efficient but produce very low thrust, so the journey would take years. Nuclear rockets are more powerful, but we haven't built or tested one in decades, and there are enormous political and safety hurdles. So we're stuck with chemical rockets for the foreseeable future. And chemical rockets, constrained by the rocket equation, make Mars missions extraordinarily difficult. The tyranny of time. But it's not just about the fuel. It's also about time. Because unlike a Moon mission, which takes about 3 days each way. A Mars mission takes months. With current propulsion technology, the most efficient trajectory to Mars, called the Hohmann transfer orbit, takes about 6 to 9 months. That's one way. Then you have to wait on Mars for the planets to align favorably for the return journey, which takes another 12 to 18 months, and then another 6 to 9 months to get back to Earth. Total mission duration, 2.5 to 3 years. Now, think about what that means. You're asking astronauts to spend 3 years in space, most of it in a cramped spacecraft, far from Earth, with no possibility of rescue if something goes wrong, exposed to hazards we'll discuss in Part 2. The International Space Station has taught us a lot about long-duration spaceflight. Astronauts have lived on the ISS for up to a year at a time. But the ISS is in low Earth orbit, only about 400 kilometers up. If there's an emergency, you can evacuate to Earth in a matter of hours. Resupply missions arrive regularly, bringing fresh food, water, spare parts, and equipment. On a Mars mission, you're on your own, completely, utterly on your own. If something breaks, you fix it with what you have, or you die. If someone gets sick or injured, you treat them with onboard medical supplies or they die. There are no resupply missions. There's no abort option once you've committed to the trajectory. And here's something most people don't realize. The return journey is actually harder than the outbound journey in many ways, because you have to carry all the fuel for the return trip with you from Earth. Or you have to manufacture it on Mars, which requires bringing an entire chemical plant with you and hoping it works perfectly with no spare parts or technical support. Think about that. You need fuel to get to Mars. You need fuel to land on Mars. You can't just crash into the surface. You need a controlled descent, which requires fuel. You need fuel to take off from Mars. And you need fuel to get back to Earth. That's an enormous amount of fuel. And all of it, except for what you might be able to manufacture on Mars, has to be lifted off Earth at the beginning of the mission, which requires even more fuel because of the rocket equation. NASA's current concept for a Mars mission involves sending cargo missions ahead of the crew, landing supplies, habitats, and fuel production equipment on Mars before the astronauts even leave Earth. This reduces the mass the crew vehicle needs to carry, but it also means multiple launches, multiple landings, and multiple systems that all have to work perfectly with no one there to fix them if they fail. It's staggeringly complex, and complexity is the enemy of reliability in spaceflight. The more components you have, the more things can go wrong. And in space, things going wrong often means people dying. The speed problem. Now, you might ask, why not just go faster? If the journey takes too long, why not develop faster propulsion systems? Good question. And the answer reveals another fundamental problem with Mars missions. To significantly reduce travel time, say from 9 months to 3 months, you need to accelerate to much higher speeds. Not just a little faster, but dramatically faster. And that means much more fuel because of the rocket equation we discussed. But there's another problem. If you're going faster, you also need to slow down when you reach Mars. And slowing down from high speeds requires just as much energy as speeding up in the first place. On Earth, when a spacecraft returns from orbit, it can use the atmosphere to slow down. That's what the space shuttle did. It would hit the upper atmosphere at high speed and use atmospheric friction to brake, converting its kinetic energy into heat. That's why you see the glowing re-entry trail. Mars has an atmosphere, but it's much thinner than Earth's, only about 1% the density. That's thick enough to cause heating during entry, but not thick enough to slow you down completely. So you still need retro rockets' engines firing in the opposite direction of travel to slow down enough for a safe landing. And remember, you're trying to land a large spacecraft with crew, life support systems, habitat modules, rovers, and all the equipment needed for a surface mission. We're talking about many tons of mass. The largest thing we've successfully landed on Mars so far is the Curiosity rover, which weighed about 1 ton. Landing something 10 or 20 or 50 times heavier is a whole different challenge. SpaceX is developing the Starship, which they claim will be capable of landing 100 tons on Mars. But it's untested, and the engineering challenges are immense. You need enormous fuel reserves for the landing, pinpoint precision to land near your pre-positioned supplies, and everything has to work on the first try because there's no second chance. The communication delay. And here's another problem that people often overlook. Communication delay. Light travels at about 300,000 kilometers per second. That's fast, the fastest thing in the universe. But space is big, really big. When Mars is at its closest to Earth, it takes light about 3 minutes to travel between the two planets. When Mars is farther away, it can take up to 22 minutes. That means if something goes wrong on a Mars mission and the crew sends a distress signal, mission control on Earth won't receive it for 3 to 22 minutes. Then it takes another 3 to 22 minutes for the response to get back. So you're looking at a 6 to 44 minute round-trip communication delay. Compare that to the moon missions. The moon is only about 1.3 light seconds away. Communication delay was barely noticeable. Astronauts could have near real-time conversations with Houston. But with Mars, real-time communication is impossible. If an emergency happens, the crew has to handle it themselves for at least several minutes, possibly almost an hour, before they can even receive advice from Earth. And during critical phases like landing or launch, that could be fatal. There's no way for mission control to intervene if something goes wrong. The crew is entirely on their own. This also affects rover operations, incidentally. The Mars rovers we've sent, Spirit, Opportunity, Curiosity, Perseverance, can't be driven in real time from Earth. Instead, engineers upload a day's worth of commands, the rover executes them, and then sends back data about what happened. It's a slow, methodical process. For a crewed mission, this communication delay means the astronauts need to be able to handle any contingency themselves. They need to be mechanics, doctors, engineers, geologists, all rolled into a small crew, and they need to carry every tool, spare part, and piece of equipment they might possibly need because they can't call for help. The psychological challenge. And then there's the psychological challenge. 3 years is a long time to be confined in a small spacecraft with the same handful of people, knowing that the nearest other humans are tens of millions of miles away, knowing that the slightest mistake could kill you. We've studied isolation and confinement extensively. Submarine crews, Antarctic research stations, simulated Mars missions in isolation facilities, and we know it's hard, really hard. People get irritable, depressed, anxious, conflicts arise, performance degrades, and that's in situations where you know you can leave if you really need to. On a Mars mission, you can't leave. You're committed for 3 years. Some research suggests that after about 18 months in isolation, psychological performance starts to seriously degrade. We don't have good data on what happens after 3 years because we've never done it. We're essentially asking astronauts to participate in an experiment we've never tried before, with their lives on the line. So even before we get to the radiation problem, which we'll discuss in part 2, we already have enormous challenges. The distance, the energy requirements, the time, the communication delay, the psychological stress, each of these alone is a major obstacle. Together, they create a formidable barrier to human Mars exploration. But wait, you might say, we've sent robots to Mars. Many of them. They've landed successfully, driven around, taken pictures, done science. If we can send robots, why can't we send people? And that's a great question. The answer is robots are much easier to send than people. First, robots don't need life support. They don't need air, water, food, or comfortable temperatures. They can survive on solar power or small nuclear batteries. They don't mind radiation. They don't get bored or lonely or scared. Second, robots can be much smaller and lighter than a crewed spacecraft. Curiosity, our largest Mars rover, weighs 1 ton. A crewed spacecraft with habitat modules, life support, and return fuel would weigh 50 to 100 tons or more. Third, robots are one-way missions. They don't need fuel to come back. That cuts the fuel requirement in half right there. And fourth, if a robot mission fails, it's disappointing but not tragic. We lose some money and scientific opportunity, but no one dies. Robots are expendable in a way humans are not. So the fact that we've successfully sent robots to Mars doesn't mean we can send people. The challenges scale up dramatically. Now, does all this mean Mars missions are completely impossible? Not necessarily. With enough money, enough time, enough technological development, we might be able to overcome these obstacles. Maybe, but it means Mars missions are far, far harder than the optimistic timelines suggest. When Elon Musk says we'll have humans on Mars in the 2030 seconds, he's either being wildly optimistic or he doesn't fully grasp the scope of the challenges. And we haven't even gotten to the biggest problem yet. The problem that might be the ultimate showstopper. The problem that, more than anything else, makes me think human Mars missions might be impossible. And that's radiation, which brings us to part 2. So let's talk about radiation, because this, more than anything else, might be the insurmountable obstacle to human Mars missions. This is the problem that keeps NASA scientists awake at night. This is the issue that doesn't have an easy solution or even a hard solution that we know how to implement. And most people don't understand just how serious this problem is. When you tell someone about the challenges of Mars missions, they think about the rocket fuel, the life support, maybe the psychological stress. But radiation? That seems abstract, technical, something engineers can solve with better shielding. Except we can't. Not easily, maybe not at all. Let me explain why. The invisible killer. First, what is radiation? In the context of space travel, we're talking about high-energy particles, protons, electrons, atomic nuclei, and various subatomic particles traveling at enormous speeds, often close to the speed of light. These particles come from 2 main sources, the sun and deep space. The sun constantly emits a stream of charged particles called the solar wind. Most of the time, this is relatively mild, but occasionally the sun has what we call solar flares or coronal mass ejections, violent eruptions that hurl enormous amounts of high-energy particles into space. If you're unlucky enough to be in the path of one of these events, you can receive a lethal radiation dose in hours. Then there's galactic cosmic radiation, high-energy particles from outside our solar system created by supernovae and other violent cosmic events. This radiation is always there, constantly bombarding everything in space, and it's incredibly difficult to shield against because the particles are so energetic. Here on Earth, we're protected from all this by 2 things, our atmosphere and our magnetic field. The atmosphere absorbs most of the radiation before it reaches the surface. And Earth's magnetic field deflects charged particles, creating the Van Allen radiation belts that trap much of the harmful radiation far above the surface. This protection is incredibly effective. Standing on Earth's surface, you receive a radiation dose of about 3 millisieverts per year from cosmic radiation. That's negligible, harmless. But in space, outside Earth's protective bubble, you're exposed to the full force of cosmic radiation. And it's brutal. Astronauts on the International Space Station, which is still within Earth's magnetic field, just at the edge of it, receive about 150 millisieverts per year. That's 50 times higher than on Earth's surface, and that's considered the upper limit of acceptable exposure for radiation workers. But on a Mars mission, you'd be traveling through deep space, completely outside Earth's magnetic field, for months or even years. And the radiation exposure is much, much worse. NASA estimates that during a typical Mars mission, 9 months to get there, 18 months on the surface, 9 months back, an astronaut would receive a total radiation dose of about 1,000 millisieverts. Some estimates go higher, up to 1,200 or even 1,500 millisieverts, depending on solar activity. Now, let me put those numbers in perspective. The career limit for NASA astronauts, the maximum cumulative radiation dose they're allowed to receive over their entire career, is set at a level that gives them no more than a 3% increase in lifetime cancer risk. For a typical astronaut, that works out to about 1,000 millisieverts total. A single Mars mission would use up an astronaut's entire career radiation allowance. And that's assuming everything goes well, no major solar events, optimal trajectory. And we're not talking about minor health effects here. Radiation at these levels significantly increases your risk of cancer. Depending on age and sex, a dose of 1,000 millisieverts increases your lifetime cancer risk by about 5%. That means if you send 20 astronauts to Mars, statistically, one of them will die of radiation-induced cancer. And that's just the stochastic effects, the probabilistic increase in cancer risk. At higher doses, you start to see deterministic effects, direct, immediate damage. Radiation sickness, damage to the central nervous system, cataracts, cardiovascular disease, cognitive impairment. There's evidence from studies of cancer patients who receive radiation therapy that high doses of radiation can cause cognitive deficits, problems with memory, attention, decision-making. Imagine astronauts arriving at Mars after 9 months of radiation exposure, needing to perform complex, life-critical tasks, and discovering their brains aren't working as well as they should. That's terrifying. Why shielding doesn't work. Now, you might think, okay, this is bad, but can't we just add more shielding? Build a thick-walled spacecraft that blocks the radiation? And that's the obvious solution, right? If radiation is the problem, just put stuff between the astronauts and the radiation. The problem is, it doesn't work. Not for cosmic radiation. And here's why. For low-energy radiation, like the X-rays you get at the dentist, simple shielding works great. A lead apron blocks X-rays just fine. Even high-energy gamma rays from nuclear radiation can be blocked with enough dense material like lead or concrete. But cosmic rays are different. These are particles, atomic nuclei, mostly protons and helium nuclei, traveling at tremendous speeds, carrying enormous amounts of energy. Some of them are traveling at 99.9% of the speed of light or faster. And when particles moving that fast hit a solid object, they don't just stop, they interact with the atoms in the shielding material, and this creates what's called a cascade shower. The incoming particle hits an atomic nucleus, shattering it and creating a spray of secondary particles, neutrons, protons, pions, other fragments. These secondary particles can be just as dangerous as the original particle, sometimes more so. So adding more shielding can actually make the problem worse. You block some of the original cosmic rays, but you create more secondary radiation. There's a sweet spot where some shielding helps, but beyond that, you're just adding mass without improving safety. And mass is the enemy in spaceflight because of the rocket equation we discussed in part 1. Every kilogram of shielding you add requires more fuel to lift it, which requires more fuel to lift that fuel, and so on. It quickly becomes impractical. To effectively shield against cosmic radiation, you'd need meters-thick shielding, preferably made of hydrogen-rich materials like water or polyethylene, because hydrogen is good at absorbing energy without creating too many secondary particles. But we're talking about tons and tons of shielding material. Some proposals suggest surrounding the crew habitat with water tanks. The water provides both radiation shielding and a consumable resource. That helps, but it's still an enormous mass penalty. Other ideas include using the spacecraft's fuel as shielding, surround the crew module with fuel tanks so the fuel blocks radiation. This works for part of the journey, but as you burn fuel, the shielding gets thinner. Or you could use Mars itself as a shield, build your habitat underground or in lava tubes. But that only protects you while you're on the surface. It doesn't help during the transit to and from Mars, which is where you receive most of the radiation dose. Solar particle events, the sudden death scenario. And then there's the acute threat, solar particle events. Most of the time, the sun is relatively quiet. But occasionally, and unpredictably, it erupts. A solar flare or coronal mass ejection can release enormous amounts of high-energy particles into space. If you're in the path of one of these events, you can receive a lethal dose of radiation in hours. We've seen some major solar events in recent history. In August 1972, between the Apollo 16 and Apollo 17 missions, there was a massive solar particle event. If astronauts had been on the moon or traveling to or from it at that time, they likely would have received a fatal radiation dose. We got lucky with the timing. In 1989, a solar event caused a massive geomagnetic storm that knocked out power grids in Quebec and interfered with satellites. In 2003, a series of solar events created what scientists call the Halloween solar storm, some of the most intense radiation storms ever recorded. These events are somewhat predictable in that we know they're associated with solar activity, which follows an 11-year cycle. During solar maximum, the peak of the cycle events are more common. During solar minimum, they're rarer. But even during solar minimum, events can happen. And we can't predict them more than a few hours in advance, if that. By the time we detect a solar flare, the particles are already on their way, arriving within hours to days, depending on the event's strength. On Earth, this isn't a problem. We're protected by the atmosphere and magnetic field. Even on the ISS, astronauts can shelter in more heavily shielded parts of the station and usually be okay. But on a Mars mission, you're in deep space with minimal shielding. If a major solar event happens, you're in serious trouble. Some mission concepts include a storm shelter, a small, heavily shielded area where the crew can retreat during a solar event. But that means cramming the entire crew into a tiny space for days or even weeks, breathing recycled air with minimal amenities. And it still doesn't guarantee safety from the most intense events. The psychological impact of knowing that at any moment, without warning, the sun could unleash a burst of radiation that could kill you, that's got to weigh on you. You're trapped in a tin can millions of miles from Earth, hoping that our star doesn't have a bad day. Radiation on Mars. Now, you might think that once you reach Mars, you're safer. You're on a planet with some atmosphere, even if it's thin. You can build shelters, maybe even underground habitats. And that's partially true. Mars's atmosphere, thin as it is, does provide some radiation shielding. Not as much as Earth's, but some. And the planet itself blocks radiation from below, so you're only exposed to radiation from above. Measurements from the Curiosity rover suggest that on Mars's surface, you'd receive about 200 to 300 millisieverts per year, about twice what ISS astronauts receive, but significantly less than in deep space. So surface habitats on Mars are somewhat better than spacecraft in transit, especially if you build underground or pile regolith Martian soil on top of your habitat for additional shielding. But here's the thing, you still have to get there and back. And that's where most of the radiation dose comes from. Even if you spend 18 months on Mars in a reasonably well-shielded habitat, you still have the 2 9-month transits through deep space where you're getting hammered with cosmic radiation. There's no way around it. The journey is the problem, and we don't have a good solution. Biological effects, more than just cancer. And it gets worse because we don't fully understand all the biological effects of long-term exposure to cosmic radiation. The cancer risk is well established. We have lots of data from atomic bomb survivors, nuclear accident victims, radiation therapy patients. We understand how ionizing radiation damages DNA and can lead to cancer years or decades later. But cosmic radiation is different from the radiation we've studied on Earth. On Earth, radiation is mostly gamma rays and X-rays, electromagnetic radiation. In space, you're dealing with high energy particles, particularly heavy ions, atomic nuclei of elements like iron, traveling at nearly the speed of light. These particles create a different kind of damage. When a high-energy iron nucleus passes through your body, it creates a track of intense ionization, damaging everything in its path. This creates what's called a microlesion, a cylinder of destroyed tissue. Your body can repair some of this damage, but not all of it. And the concern is that these heavy ions might cause damage that leads to health problems we don't fully understand yet. Studies on mice exposed to simulated space radiation have shown effects beyond cancer, cognitive deficits, cardiovascular disease, accelerated aging, immune system dysfunction, even behavioral changes. Some research suggests that cosmic radiation exposure might increase the risk of Alzheimer's-like dementia, that astronauts might return from Mars cognitively impaired with memory problems, difficulty concentrating, personality changes. And we don't know for sure because we've never exposed humans to these radiation levels for these durations. We're extrapolating from animal studies and cell cultures and mathematical models. We might be underestimating the risk. Or maybe we're overestimating it. We simply don't know. And that uncertainty is itself a problem. How do you ethically send astronauts on a mission when you can't tell them with confidence what the health consequences will be? Genetic damage in future generations. There's also the question of genetic damage. Radiation can damage DNA and reproductive cells, sperm and eggs, potentially causing mutations that could be passed on to children. If you send astronauts to Mars and they receive significant radiation doses, we don't know what that means for their ability to have healthy children afterward. There might be increased risk of birth defects, genetic disorders. This is particularly concerning if the goal is to establish a permanent settlement on Mars. If the colonists are constantly exposed to higher radiation levels than on Earth, what does that mean for their descendants? Will successive generations accumulate more and more genetic damage? On Earth, evolution has optimized our DNA repair mechanisms for the radiation levels we experience here, but on Mars, with higher radiation, those mechanisms might not be sufficient. Over generations, you might see increased cancer rates, shorter lifespans, higher infant mortality. We simply don't know, and we won't know until we try, which means using humans as experimental subjects in an unprecedented way. The fundamental problem, time. Here's the core issue with radiation. It's a function of time. The longer you're exposed, the more dose you accumulate. And there's no way to speed up a Mars mission significantly with current propulsion technology. If we could get to Mars in a few weeks instead of 9 months, the radiation problem would be much more manageable. But as we discussed in part 1, going faster requires dramatically more fuel because of the rocket equation, and we're already at the limits of what's practical with chemical rockets. Advanced propulsion systems, nuclear thermal rockets, ion drives, even theoretical fusion drives could potentially reduce transit times. But these technologies are decades away from being ready for crewed missions, if they ever become practical at all. So we're stuck with long transit times, which means high radiation doses, which means serious health risks that we don't know how to adequately mitigate. NASA's dilemma. And this puts NASA in an impossible position. They have a mandate to explore, to push boundaries, to send humans to Mars. But they also have a responsibility to keep astronauts safe. The current NASA standard is that the increased cancer risk from radiation exposure should not exceed 3% over an astronaut's career. A Mars mission would blow past that limit. So NASA has a few options. One, develop better shielding technology. But as we've discussed, this is incredibly difficult and might not be possible with known physics. Two, develop better propulsion to reduce transit time, but that's also incredibly difficult and far from ready. Three, accept higher risk levels. Change the standards. Allow astronauts to take on more cancer risk in exchange for the opportunity to go to Mars. NASA has actually been moving toward option 3. They've convened committees to study whether the 3% limit is too conservative, whether it should be raised to 5% or even higher for Mars missions. And maybe that's reasonable. After all, we allow astronauts to take risks. Going to space is inherently dangerous. Rockets can explode. Spacecraft can malfunction. Any number of things can go wrong. Astronauts accept these risks because they believe the mission is worth it. Maybe radiation risk should be viewed the same way. It's just another hazard of the job. If astronauts are willing to accept a higher cancer risk in exchange for going to Mars, should we let them? There's an ethical debate here. Some people say yes, informed consent, personal choice. These are adults making decisions about their own lives. Others say no, we shouldn't be asking people to accept almost certain serious health consequences for a mission that, while scientifically and symbolically important, isn't actually necessary for human survival. And there's no clear answer. The problem might be unsolvable. But here's what keeps me up at night. The radiation problem might simply not have a solution. Not with physics as we understand it, not with technology we can realistically develop. To adequately shield against cosmic radiation, you'd need either meters-thick shielding, which is impractical due to mass constraints, or active shielding using magnetic fields to deflect charged particles, which requires enormous amounts of power that we don't know how to generate in space, or dramatically faster propulsion to reduce exposure time, which requires breakthrough physics we don't have. None of these solutions are on the horizon. They're all theoretical, speculative, far future technology. So with current or near-term technology, we can't adequately protect astronauts from radiation on a Mars mission. We can reduce the dose somewhat with clever design, water shielding, storm shelters, but we can't eliminate the risk. We probably can't even get it down to acceptable levels by NASA's current standards, which means either we accept that Mars astronauts will face serious health consequences, cancer, cognitive impairment, possibly early death, or we don't send humans to Mars. And that's not a decision anyone wants to make. Because the dream of Mars is so compelling, the idea of humans walking on another planet, of becoming a multiplanetary species, it's inspiring, it's ambitious, it speaks to our deepest instincts as explorers and pioneers. But dreams run into reality. And the reality is that space is hostile to human life in ways we can't easily overcome. Now, you might ask, what about sending robots instead? Why risk human lives when we can send robots to do the science? And that's a very good question. Robots have been incredibly successful on Mars. They don't need radiation shielding, life support, or return trips. They can work for years, exploring, analyzing, sending back data. The Perseverance rover is currently searching for signs of ancient life on Mars. It's collecting rock samples that will eventually be returned to Earth by future missions. It's doing groundbreaking science without risking any human lives. So why send humans at all? What can humans do on Mars that robots can't? The argument is usually that humans are more flexible, more adaptable, better at making decisions in the field, better at complex scientific work. A human geologist can make observations and connections that would take a robot much longer to make if it could make them at all. And there's something to that. But is it worth the risk? Is it worth potentially killing or seriously harming astronauts just to do the science slightly faster or slightly better? I don't know. It's a hard question. But what I do know is that the radiation problem is not going away. It's not something we can solve by throwing more money at it or developing incrementally better technology. It's a fundamental barrier imposed by physics. And unless we develop radically new propulsion systems or find some way to generate powerful magnetic shields in space, both of which seem far beyond our current capabilities, radiation will remain the ultimate showstopper for human Mars missions. But let's suppose, for the sake of argument, that we solve the radiation problem somehow. Maybe we accept higher risk levels, maybe we develop better shielding, maybe we get lucky and find a way to make it work. Even then, we face enormous challenges once we actually reach Mars and try to live there. And that brings us to part 3, survival on the surface and the nearly impossible challenge of coming home. So let's imagine we've solved the distance problem. We built a massive rocket, overcome the tyranny of the rocket equation, accepted the months-long journey, and let's imagine we've solved, or at least accepted, the radiation problem. We've equipped our spacecraft with the best shielding we can manage, we've built storm shelters, and we've convinced astronauts to accept cancer risks that would horrify any medical ethics board. Against all odds, our crew arrives at Mars. They've survived the journey. They're in orbit around the red planet, looking down at the rusty surface, seeing Olympus Mons, the largest volcano in the solar system, and Valles Marineris, a canyon that makes the Grand Canyon look like a ditch. Now comes the really hard part, landing, living, and most impossible of all, coming home. The landing problem. Let's start with landing, because this is much harder than most people realize. Mars has an atmosphere, but it's incredibly thin, about 1% the density of Earth's atmosphere. That's thick enough to cause serious heating during entry, but not thick enough to slow you down effectively. On Earth, when a spacecraft returns from orbit, it can use the atmosphere to brake. The space shuttle would hit the upper atmosphere at 17,000 miles per hour and use atmospheric drag to slow down, converting kinetic energy into heat. That's why you see the glowing re-entry trail. On Mars, the atmosphere is so thin that it can't do the job alone. You still get the heating. In fact, you get intense heating because you're coming in fast from an interplanetary trajectory, but you don't slow down enough. By the time you reach the lower atmosphere, you're still going way too fast to land safely. So you need retro rockets. Engines firing in the opposite direction of travel, burning fuel to slow you down. And you need a lot of fuel because you're trying to land something heavy, not a 1-ton rover like Curiosity, but a crewed spacecraft with habitat modules, life support systems, supplies, and all the equipment needed for surface operations. We're talking about landing 20, 50, maybe 100 tons on Mars. We've never done anything close to that. The largest thing we've successfully landed on Mars is Curiosity at 1 ton, and that required a complex system called the Sky Crane, a rocket-powered platform that lowered the rover on cables. It worked miraculously, but it was nerve-wracking, and it was for just 1 ton. Scaling that up to 20 or 50 tons is a completely different engineering challenge. You need much larger engines, much more fuel, much more precise control. And you're doing this after months in space with equipment that's been exposed to radiation and cosmic rays and temperature extremes that hasn't been serviced or maintained. One failure, one engine that doesn't ignite, one sensor that gives bad data, and you crash. And unlike robotic missions where a crash is disappointing but not tragic, here you've just killed your entire crew. SpaceX's Starship is designed to land on Mars using a belly flop maneuver, entering the atmosphere horizontally to maximize drag, then flipping vertical at the last moment and firing engines to land. It's an audacious concept. They've tested it on Earth with mixed results. Several test flights ended in spectacular explosions, and that's on Earth, where they can iterate, where they can analyze failures and try again, where the atmosphere is 100 times thicker than Mars's. Doing this on Mars, where you have one chance and failure, means death is terrifying. The dust problem, and then there's the dust. Martian dust is everywhere, and it's a serious problem. Unlike Earth dust, which is rounded and weathered by water and wind over millions of years, Martian dust is sharp and angular. It hasn't been weathered because there's almost no water on Mars, and it's incredibly fine particles, smaller than talcum powder. This dust gets into everything. The rovers have struggled with it. Solar panels get covered, reducing power. Mechanical joints get clogged. Seals get compromised. For a crewed mission, this is a major hazard. Dust will get into the habitat even with the best airlock procedures. And Martian dust is toxic. It contains perchlorates, chemical compounds that are harmful if ingested or inhaled. Breathing Martian dust could cause serious lung damage. The Apollo astronauts experienced something similar with lunar dust, which also got everywhere despite their best efforts. They described it as smelling like gunpowder, and some experienced respiratory irritation. But they were only on the moon for a few days. On Mars, you'd be dealing with this for 18 months or more. The cumulative health effects could be serious. And during dust storms, which can be planet-wide on Mars, lasting for months, visibility drops, solar power is reduced or eliminated, and the dust becomes even more of a problem. You'd essentially be trapped in your habitat, hoping your life support systems don't fail, waiting for the storm to pass. The survival challenge. Speaking of life support, let's talk about what it takes to keep humans alive on Mars. You need air. Oxygen, specifically. Mars's atmosphere is 95% carbon dioxide, about 3% nitrogen, 1.6% argon, and only trace amounts of oxygen. You can't breathe it. So you need to either bring oxygen from Earth or make it on Mars. Bringing it is impractical. Oxygen is heavy, and you'd need a lot of it for 18 months, so you make it. The MOXIE experiment on the Perseverance rover has demonstrated that you can extract oxygen from Mars's CO2 atmosphere using electrolysis. It works, but it requires power, lots of it. And you need a robust system that won't break down, because if your oxygen production fails, you die. You need water. Mars has water frozen at the poles, probably as ice beneath the surface in some regions. But extracting it, purifying it, and storing it requires equipment, power, and constant maintenance. The plan is usually to recycle water as much as possible, capture humidity from breathing, recycle urine and wastewater. The ISS does this already, but systems fail, filters clog, pumps break. On the ISS, you can get replacement parts on the next resupply mission. On Mars, you fix it with what you have, or you run out of water and die. You need food. You can bring some from Earth, but for an 18-month surface stay, that's a lot of food. Hundreds of kilograms per person. The alternative is growing food on Mars, which sounds great until you think about the challenges. Martian soil is toxic. Remember those perchlorates. You'd need to either decontaminate it or bring soil from Earth or grow plants hydroponically. You need light, either sunlight through transparent structures or artificial grow lights, which require power. You need temperature control. Mars is cold, averaging around negative 60 degrees Celsius, negative 80 degrees Fahrenheit. Plants don't grow in those conditions. You need a controlled environment, which means habitats with heating, lighting, humidity control, nutrient delivery systems. And all of this needs to work perfectly for 18 months while exposed to Martian dust, temperature extremes, and radiation. NASA and others have done experiments growing plants in simulated Martian conditions. It's possible, but it's incredibly difficult and energy intensive. You need power, lots of it, for life support, for oxygen production, for water recycling, for heating, for lighting, for charging rovers and equipment, for running experiments. Solar power is the obvious choice. Mars gets sunlight, though it's weaker than on Earth because Mars is farther from the sun. But solar panels get covered with dust, reducing efficiency. And during dust storms, solar power drops to nearly zero. The alternative is nuclear power, small nuclear reactors that can provide steady power regardless of weather or time of day. NASA has developed the kilopower reactor, a small fission reactor designed for space missions. It works, but you're bringing radioactive material to Mars, setting up a nuclear reactor, and hoping it doesn't malfunction. And you need redundancy for everything. If your oxygen system fails, you need a backup. If a habitat module loses pressure, you need another one. If a power system goes down, you need alternative power sources. Every single system needs to be robust, reliable, and ideally have multiple backups, because you can't call for help. You're on your own for 18 months until the launch window opens for the return trip. The isolation and psychological toll. And then there's the psychological challenge of being on Mars. You're 150 million kilometers from Earth, give or take. You can see Earth in the night sky, a blue dot, barely visible. You know that everyone you've ever known, everyone you love, every human except for the handful with you is on that distant dot. Communication has a 20-minute round-trip delay. You can send messages home, but conversations are impossible. You send a message, wait 20 minutes for a response. Send another message, wait another 20 minutes. It's asynchronous, disjointed, frustrating. You're confined to a small habitat, probably not much bigger than a few shipping containers connected together. You can go outside, but only in a bulky spacesuit for limited periods, doing specific tasks. There's no fresh air, no rain, no wind on your face, no trees, no birds, no life at all, except what you brought with you. Just red rocks and dust as far as you can see. The monotony would be crushing, the isolation would be intense, and you're stuck there for 18 months, knowing that if something goes wrong, if you get seriously sick, if there's an accident, if a critical system fails, there's no rescue, no one can reach you. You either solve the problem or you die. Studies of isolated groups, Antarctic research stations, submarine crews, simulated Mars missions show that psychological problems emerge. Depression, anxiety, interpersonal conflicts, sleep disturbances, cognitive deficits. And that's in scenarios where people know they can leave if absolutely necessary, where they know help can arrive in days or weeks if there's a true emergency. On Mars, there's no escape hatch. You're committed for 18 months. And then you face the hardest part of all, the journey home, the return journey, the ultimate challenge. Here's what most people don't realize. The return journey from Mars is actually harder than the trip there. Much harder. Why? Because you need fuel to get off Mars, to escape Mars's gravity, and to make the journey back to Earth. And that fuel either needs to come from Earth, which means you had to carry it all the way to Mars, which drastically increases the mission mass and complexity, or you need to make it on Mars. Making fuel on Mars is the preferred approach, and it's called in situ resource utilization, or ISRU. The idea is to use Martian resources, specifically the CO2 atmosphere and water ice, to produce methane and oxygen, which can be used as rocket fuel. The chemistry is well understood. The Sabatier reaction combines CO2 and hydrogen to produce methane and water. Electrolysis splits water into hydrogen and oxygen. With enough power and the right equipment, you can produce rocket fuel on Mars. SpaceX's Starship is designed to use methane oxygen fuel specifically because it can be produced on Mars. The plan is to send fuel production equipment to Mars ahead of the crew, start producing fuel, and have a full tank ready for the return trip by the time the astronauts arrive. Sounds great, right? Except for the minor detail that this has never been done. We've never produced rocket fuel on another planet. We've never run an automated chemical plant remotely for 2 years while waiting for astronauts to arrive. We've never tested whether Martian water ice can be reliably extracted and purified at the scales needed. And if it doesn't work, if the fuel production fails, if you don't produce enough fuel, if the fuel quality isn't adequate, then the crew is stranded. They can't come home. Think about that. You've sent humans on a one-way trip hoping that untested technology will work well enough to get them back. Now, you could bring all the return fuel from Earth, but that creates a mass problem of staggering proportions. You'd need to launch not just the crew and their habitat and supplies, but also tens of tons of rocket fuel. And to lift that much mass off Earth, you'd need even more fuel because of the rocket equation. It becomes a vicious cycle. You need fuel to bring fuel. Some analyses suggest that a fully fueled Mars mission using Earth-supplied return fuel would require a launch mass of thousands of tons, far beyond anything we can currently launch. So ISRU isn't just a nice-to-have feature. It's absolutely essential. The mission doesn't work without it. And that means betting astronauts' lives on technology that's never been tested in real Martian conditions. Launch from Mars. Assuming you've somehow produced the fuel, you now need to launch from Mars. Mars's gravity is about 38% of Earth's, so it's easier to launch from Mars than from Earth. But it's still a significant challenge. You need a rocket, a launch pad, fuel loading systems, all of which have been sitting on Mars for 18 months, exposed to dust, temperature, extremes, and radiation. Everything has to work perfectly on the first try. There are no test launches, you can't practice, you launch or you stay on Mars forever. And you're launching not just a small capsule, but a spacecraft large enough to sustain the crew for the 9-month journey back to Earth, with all the life support, food, water, and supplies they'll need. The Apollo astronauts launched from the moon using the lunar module's ascent stage, a relatively small spacecraft, because the moon's gravity is only 16% of Earth's, and they only needed to reach lunar orbit, not travel back to Earth. Launching from Mars requires something much larger and more complex. And if the launch fails, if an engine doesn't fire, if the trajectory is wrong, you're either stuck on Mars or you're in a bad orbit that doesn't get you home. The journey back, and then, assuming you successfully launch from Mars, you face another 9-month journey through deep space with all the radiation exposure we discussed in part 2, except now you're exhausted from 18 months on Mars. Your body has been exposed to Martian dust, low gravity, high radiation. Your psychological reserves are depleted. Your equipment has been running for over 2 years and is showing wear. And you're coming home to Earth, which means you need to hit a very precise re-entry corridor, too shallow, and you skip off the atmosphere back into space, too steep, and you burn up from excessive heating. The Apollo missions had to hit a re-entry corridor about 40 kilometers wide from a distance of 400,000 kilometers. That's like shooting an arrow in New York and hitting a target the size of a building in Los Angeles. Incredibly precise. A Mars return requires similar precision, but after a 9-month journey during which your trajectory could have been affected by small errors in navigation, micrometeorite impacts, equipment drift, and you're doing this when you're physically and mentally exhausted, when your equipment might be degraded, when you've been away from Earth for nearly 3 years. The physical cost. Speaking of physical effects, let's talk about what 3 years in space does to the human body. We know from ISS experience that long-duration spaceflight causes bone density loss. Astronauts lose about 1 to 2% of bone mass per month in microgravity. Over 3 years, that's potentially 30–70% bone loss. Your bones become fragile, brittle. Some of this recovers after returning to Earth, but not all of it. Muscle atrophy. Without gravity to work against, muscles weaken. Even with exercise, and ISS astronauts exercise 2 hours a day, there's significant muscle loss. Cardiovascular changes. The heart doesn't have to work as hard in microgravity, so it weakens. Blood pressure drops. When you return to Earth's gravity, standing up can cause fainting because your cardiovascular system has adapted to 0 G. Vision problems. Many astronauts experience vision degradation in space due to fluid shifts that increase pressure on the optic nerve. Some of this is permanent. Immune system suppression. Spaceflight weakens the immune system, making you more susceptible to infections. Kidney stones, the combination of bone loss, releasing calcium, dehydration, and fluid shifts increases kidney stone risk. And that's from missions lasting 6 months to a year on the ISS, where astronauts can return to Earth relatively quickly if there's a medical emergency. On a Mars mission, you're gone for 3 years. The bone loss alone could be crippling. Astronauts might return unable to walk, their bones so weak that they fracture easily. They might have permanent vision damage, cardiovascular problems, cognitive deficits from radiation exposure. We're potentially sending people on a mission that will permanently damage their health, even if everything goes perfectly. The ethical question. And this brings us back to ethics. Is it right to ask people to accept these risks, to potentially sacrifice their health, their remaining years of life for a Mars mission? Some people say yes. Explorers throughout history have taken enormous risks. Magellan's crew sailing around the world, Shackleton's Antarctic expedition, the early test pilots and astronauts, all of them faced potentially fatal risks for the sake of exploration and discovery. And if astronauts fully understand the risks and choose to go anyway, shouldn't we respect that choice? But there's a difference between risking death in an accident and accepting near certain long-term health damage. The radiation exposure alone almost guarantees increased cancer risk. The bone loss, muscle atrophy, cardiovascular changes, these are inevitable, not just possible. We're not just asking astronauts to brave danger. We're asking them to accept significant, permanent health consequences. Is that ethical? I honestly don't know why Mars might be impossible. So let me bring all of this together and explain why I think Mars missions might be genuinely impossible with foreseeable technology. It's not any single problem. It's the combination of problems, each one difficult, all of them together potentially insurmountable. The distance and energy requirements mean missions take years and require enormous amounts of fuel. The radiation exposure is severe and we don't have a good way to shield against it. Landing on Mars requires technology we've never demonstrated at the necessary scale. Surviving on Mars for 18 months requires complex systems that all have to work perfectly with no possibility of resupply or rescue. Producing return fuel on Mars using ISRU is unproven and might not work reliably. Launching from Mars after 18 months of equipment exposure to harsh conditions is risky. The return journey exposes astronauts to more radiation and requires precise navigation. Re-entry to Earth after a 3-year mission with degraded equipment and exhausted crew is dangerous. And the cumulative health effects, radiation, bone loss, muscle atrophy, psychological stress, might be permanently damaging. Any one of these could be overcome with enough effort, money, and technological development. But all of them together, that's a much harder proposition. And we haven't even talked about cost. NASA estimates that a human Mars mission would cost somewhere between $100 billion and $500 billion, depending on the mission architecture and how you account for development costs. That's an enormous sum, even for a government program. For comparison, the entire Apollo program cost about $280 billion in today's dollars. And that was for a mission that took 3 days each way, not 9 months. A Mars mission would be far more complex and expensive. Is it worth it? Is the scientific return, the inspirational value, the symbolic importance of humans on Mars worth hundreds of billions of dollars, and the near certain health damage to the astronauts? Reasonable people can disagree, but the cost-benefit analysis is not obviously in favor of sending humans. The alternative, robots. And this is why I keep coming back to robots. Because robots can do much of the science we want to do on Mars without the enormous cost and risk of human missions. The Perseverance rover is currently exploring Jezero Crater, searching for signs of ancient microbial life, collecting samples that will eventually be returned to Earth. It cost about $2.7 billion, a lot of money, but a tiny fraction of what a human mission would cost. We could send dozens of rovers, landers, orbiters, sample return missions for the cost of one human mission. We could explore multiple sites simultaneously. We could take risks with robots that we'd never take with humans. Yes, humans are more flexible and adaptable than robots. A human geologist could make observations in minutes that would take a rover days or weeks. But is that worth the cost and risk? I'm not sure it is. At least not with current technology. The path forward. Now, does this mean we should give up on human Mars exploration entirely? Not necessarily. But it means we need to be realistic about the challenges and the timelines. When people talk about humans on Mars in the 2030 seconds, they're being wildly optimistic, probably delusional. We need major technological breakthroughs before human Mars missions become feasible. Better propulsion systems to reduce transit time and radiation exposure, better radiation shielding or medical countermeasures. Proven ISRU technology demonstrated at scale on Mars. Better life support systems that can run reliably for years. Solutions to the bone loss and muscle atrophy problems of long-duration spaceflight. Some of these might be achievable in decades. Some might require breakthrough physics we don't have. In the meantime, we should focus on what we can do. Continue robotic exploration of Mars, including sample return missions. Establish a permanent presence on the Moon, which is much closer and allows us to test technologies in a place where rescue is at least theoretically possible.